Hey, what's going on, guys? Coming here. In this video we're going to learn how to subtract two 16-bit numbers in 652 assembly. So just like in the previous video where we've been doing addition, it's all about dealing with the carry flag. So let's go for a simple experiment first. So like most of the programs in 652, I'll start with clearing the decimal flag to make sure that subtract would be working for 16-bit for hexadecimal numbers and not trying to emulate the decimal mode. And then let's clear the carry. So CLC, and then just assemble this to 200s and upload, and 200s and Shift G to execute, and I'm going to F1, and this is the status data. This is the status register, just the standard place for a status register to F1 status register. And to decode this, we can get the value of the carry flag. So we need to turn this number into binary. So 30 in hexadecimal would be 001100, and the row last byte is this carry flag, so it's equal to 0. However, if we do this here, we do the set carry flag and do exactly the same thing in upload and 200 space Shift G and F1, then we have 31. So 31 goes like this. So now we got this carry flag being set. Now, what is interesting about the subtract itself, so let's consider we're loading the value of, let's say, I don't know, 0.9 to the accumulator, and say subtract with carry the value of 1. And let's assemble the program and upload to hundreds, Shift G to execute, and now we see this F3 to see what the A register of the accumulator is currently equal to. So F3, here we have the result 0.8, which is exactly the case because 9 minus 1 is going to be 8. However, this behavior only happens in case if this carry flag is being set. If, for instance, we clear the carry flag like this, assemble and upload and 200s and Shift G and F3 for the result, here we have 7, so it's like 9 minus 1 and minus carry flag. So 9 minus 1 is 8, and minus carry flag, another 1 is going to be like 8 minus 1 is going to be 7. Even though so if the carry flag is cleared here, then it's being subtracted by the subtract instruction. Now, the reason why this is happening actually, well, that's used in order to handle the following case. So let's imagine that we have the following scenario. So we just set the carry flag, and we have this we have 0 in the accumulator, and then we do this minus 1. So let's have a look what the result would be in this case. 200s upload, 200s Shift G and F3. So it's equal to FF because the values are wrapping around, so 0 minus 1 is going to be FF. But meanwhile, now you remember we set the carry flag before running all of this stuff, but if we just go to F1, then we see that it's already it's B0. B0 stands for, B0 is negative flag is being set, then expansion flag break, and the carry flag is not being set actually. So this is what we have if we decode this value. So this means that the turn of carry flag from 1 to 0 indicates the fact that the wraparound has occurred, and we can use this kind of feature in order to subtract our 16-bit numbers. So for instance, let's go the following way. If I now say again LDA, well, let's actually try 2 minus 5, for instance, like this, and assemble and upload 200s and F3. So we have this FD, which makes sense. But what about the carry flag? So this is only the low bit of the 16-bit value. So what about the low byte of the 16-bit number? So what about the high byte? So we say LDA and 00, And now without clearing the without setting the carry, so it's better to say that the carry is actually set before the SBC itself occurs, right? So here instead we're not saying we're not setting carry. Instead we're doing SBC and the value of 0. And in case if the carry flag is still being set, this won't actually change the value of the A register. However, if it's been cleared, then it would change the value. So now if I just define the print byte constant, which is the address of 1E3B, which is specific to key monitor, to output whatever we have in the A register to the serial port to print the value of the A register as to hexadecimal digits to the serial port. So in this case, for instance, so here we have the low byte, and let's actually store this to result low, and this store to result high. Now let's define those as well. So result low, and just define an empty byte there, and result high, and just define an empty byte there as well. So here we're done with calculating the lower bit, and actually better making like this, and storing this. And here we're dealing with calculating the high bit and storing it as well. So since the high bit is already in the A register, we can already print this. So gem subroutine print byte, and then we want to load the low register that has been stored previously, and gem subroutine to print byte here as well. So let's assemble and upload, and 200s, Shift G, and we have FFFD as the result. So check this out by the calculator. So programming mode, I'd say 0002 minus 0005, but it doesn't make sense print -3, right? So I actually want to see the 2's complement of -3, the 2's complement of -3, which is, so it's much bigger than 16-bit digits. So we only need this last 4 digits here, which is exactly the same as our result. So now you might be wondering how to apply this to perform a subtraction between two actual numbers. So let's try that as well. So for this, I want to define num1 high bit, and define byte high byte, and define like this. Num1 high, num1 low, num2 high, num2 low. So first we say LDA. So first we want to deal with low with a lower byte, and then with a higher byte. So LDA num1 lower byte, and set carry flag, and subtract num2 lower byte. And then we want to store this to result low, right? Then we want to say we want to load the num1 high bit, and then without setting the carry again, because if the overflow occurs, we already know that. So we just need to say subtract with carry num2 high, and want to store this as the result high. And since the result high is already there in the A register, we can just simply jump to some subroutine print byte, and then want to load the lower byte. So load result low, and jump to subroutine print byte. And all we need here is just to set the values. So let's say the upper bytes like this. If upper bytes, if this would be less than this one, then we're just running out of 16 bits, and we'll need implement the 32-bit arithmetics, which goes beyond the scope of this tutorial. So make sure that in the 32-bit mode it doesn't go negative. That is with this example in particular. But here, let's do the same too, and here maybe even some bigger numbers. So 6502, this is cool, 6502 minus 2423. Okay, so let's assemble this and upload. The 6502 wasn't intentional, really. 200s and Shift G, and we have the result 40DF. So now let's make sure this actually works. So open the calculator. So I want the 2's complement. Also need the parentheses for otherwise it's not going to be working properly. So 6502. Okay, again 2's complement. 6502 minus 2423 and equals, something has gone horribly wrong somewhere. Did it mess up? Hold on. Guys, I'm sorry, I'm an idiot. I didn't need to use the 2's complement, obviously, because the resulting number is not going to be negative. It's only was negative for the lower byte, but for the overall number, it's not. So just the result is actually 40DF, so it just didn't need to apply the 2's complement to this. Sorry for that. So yeah, this is how we can subtract two 16-bit numbers using the 6502 assembly. So I hope you've enjoyed the tutorial. And found something interesting in it. This is it from my side. Thanks for watching. Until the next time, and take care.